Summer 6 weeks. Okay, here we go, folks. Let's get to it. All right, let me move some stuff around here on my screen. Previous. Zoom keeps changing stuff. I got all kinds of different toolbars all the time. It's like, come on, man. All right. Chemistry. Chemistry is a physical science, which means, yes, how physical science is different than life sciences like bio? Well, we like math. So we don't like math as much as physics, but we like math here in chem, and there will be plenty of math to go around. You'll see that math tonight. The physical sciences try and take nature and reduce it to some mathematical function. Can we use math to predict what's going to happen in the future? Or can we use a mathematical formula to explain why something is happening? Chemistry specifically deals with matter and its changes. And we're going to get into all that tonight. Physical changes, chemical changes, that's coming super duper soon. We should probably define matter since chemistry studies matter. Matter is anything that has a mass and takes up space. And if you think about it, it's hard to do one of those without the other, right? If you have a mass, you probably exist. And if you exist, you probably have a mass, right? So things that don't have a mass and take up space, well, that's pretty much energy. And we chemists dabble in energy from time to time. Like when we get into thermo, we'll talk about how chemical reactions, when you break bonds and release and make new bonds, how that can, absorb energy and release energy to the environment. We'll get into all that, but we kind of try to leave that energy stuff and we're going to, light is coming next week. We'll talk about the electromagnetic spectrum, emissions in the hydrogen atom. So we definitely do talk about energy, but our main focus in this class is matter. Matter exists in 4 main states. That's solid, liquid, gas, and maybe you've heard of the 4th one, plasma, which we'll talk about in a moment. Plasma is just super hot gas that has lost some electrons. There are weirder states of matter. So Bose-Einstein condensates, fermionic condensates, those are the weirder ones. So let's talk about these different states that matter can take on. So solid, liquid, gas. Every single one of you obviously knows what a solid is. You know what a liquid is. You know what a gas is. Here's the trouble, right? If I, clear this screen and I say, if I go back and I say, okay, what makes a liquid unique? What makes a liquid a liquid? How is it different than the other states of matter? Write that down in a sentence. That can get tricky sometimes, right? So, while we all know what a solid, a liquid, and a gas are, can you define them, right? What really makes them unique? Well, solids, everything is locked in. A solid has a definite shape, has a definite volume. It is locked in. Liquids only have a definite volume. They do not have a definite shape. So if you think about it, when you put a liquid in a container, it just takes on the shape of the bottom of that container, right? 30 milliliters of water is 30 milliliters of water, but that's going to look different in this cup. Then it's going to look spilt on the table. Then it's going to look in a slurpy straw, right? The shape is not set. Gases are special. Gases, and that's why they get an entire chapter, right, that we do near the end of this course. Gases don't have anything locked in. Gases will spontaneously fill any container you put them in. So a gas's volume depends on the container, and its shape depends on the container as well. Oh, I should talk about plasma. Plasma. We never talk about plasma, right? But it is the most abundant state of matter in the universe, not on Earth, but in the universe, right? Where is all this plasma? Stars. Stars are giant plasma balls, right? And in most solar systems, that's where most of the mass is, right? I mean, our sun, I forget how many Earths you can fit in the sun. It's something crazy, right? I mean, every time I read that, it blows my mind. Astronomy used to be a hobby of mine, but I don't have time for it because I already don't sleep enough, so I can't stay up that late anymore. I just can't do it. Anyway, plasma is super hot gas. It was so hot that electrons have been kicked out of it. So now the gaseous particles are not neutral anymore. They have a charge. And now they repel each other and attract each other. And it just has unique, stuff. Plasma does exist on Earth. Lightning strikes. When lightning strikes, it is able to ionize the molecules in the air. Air is a homogeneous mixture of gases. So it's able to create plasma around that lightning strike for a very brief period of time. And I've also heard volcanoes, when they erupt, And also, they're so energy intensive, they can create plasma around them as well. And obviously, in the lab, we can create plasma too. Atoms, elements, compounds, molecules. Let's get that all out in the open. Let's talk about atoms, elements, compounds, all that stuff. On Wednesday, before we get into nomenclature, we're going to get into the history of chemistry, and a lot of that history of the chemistry deals with atoms, right? So, like, how did we figure out what the atom looks like and all that jazz? This is actually a picture of xenon atoms. This was done, I believe, in the 90s. You can see who funded this. Obviously, IBM funded this research. This group was able to plate individual xenon atoms on this surface, and then they took a picture of it with a scanning tunneling microscope. Each one of those cones is a different xenon atom. You say, why would you want to plate individual xenon atoms on a surface? Well, can you imagine the smallest computer processor could be one atom thick, right? And that's why IBM was funding all that research. So atoms are like the building blocks that matter is made of, right? And we'll get into atoms and talk about their structure and all that stuff next time. But I want to get some clear definitions down: elements, compounds, molecules. So let's do that on the board. Oh, Sophia got booted. We're gonna let her back in. Let's get some definitions. Let's write some stuff down. I need to stand. I'm tired of sitting. Let's get into this. Here we go. Elements. Elements contain one type of atom. Keyword here, keywords, one type. Notice I didn't say one atom. They can contain one atom. So for example, you could have an individual iron atom, okay? But that's not where elements stop. For example, the element that's keeping you alive right now is actually a diatomic element, and that element is O2. Notice how this still fits our definition for an element. It's two atoms, but they're both oxygen, so it's one type of atom, right? Sulfur usually comes as 6. The one elemental form of carbon that we're going to talk about here in a moment, Buckminster fullerene, that's 60 carbon atoms. Those are all elements. You don't have to be just one atom, but you got to be one type of atom. The next thing is a compound. And compounds contain at least 2 different types of atoms. Compounds contain at least 2 different types of atoms. Compounds, oh my goodness. So for elements, right, there's only 118 different elements, and there's only so many ways you can bring them together, right? Like O2 and O3, like oxygen on Earth is either O2 or O3, right? So oxygen only has 2 elemental forms, molecular oxygen and ozone. So, maybe there's at most 400 different ways you can arrange the elements, pure elements. Compounds, though, we have like 5 million. Okay, now a lot of them are organic, which you might have to take, in a year or so, or maybe even this fall, doubled up with 102. But there's so many more compounds, right? And pretty much Wednesday's lectures would be like, how do we name these compounds? But a compound contains 2 different types of atoms. So let's just look at some examples. So something like carbon monoxide, that contains 2 different atoms, and they're, that would be like the minimum for a compound, right? Now you got to be careful with your capitalization, okay? Capital C, capital O, that's a compound. Capital C, lowercase o, that's an element, that's cobalt. So you really got to watch out for that capitalization, right? Okay, if an element has 2 letters, that second letter must be lowercase, okay? You got to be really, really careful. You kind of got to exaggerate. CO2, there's another one, right? So that's a carbon, and again, it's 2 different types of atoms. Water is a compound, H2O. Glucose, C6H12O6. Those are all, table salt, sodium chloride. Those are all compounds, 2 different kinds of atoms. Another really important word that I don't have on the slides there is molecules. And molecule is a special word that can sometimes talk about elements and sometimes refer to compounds. It can refer to both. A molecule just indicates that the thing contains at least two atoms. And you say, whoa, what's the difference between molecule and compound? Compounds have to have at least two different types, okay? A molecule just has to contain at least two atoms. So you can have molecular elements and you can have compounds that are molecules, right? So for example, O2, that's a molecule and an element, right? CO2, that's a molecule and a compound. So molecule is the broader term, okay, that I think a lot of times people want to use the word molecule to talk about something like O2 and they'll accidentally use compound. So molecule is a big word to use there too. All right. I'm digging it. So we did elements. Some atoms only have one elemental form on Earth, and other elements can have, 5, 6, 7 different elemental forms. Carbon is a great example of this. Carbon on Earth for like 200 years, we thought only came in two forms, pure carbon. We thought it came as graphite. Some of you might be writing with that right now if you have a pencil. And then we thought it came as diamond, right, which forms under higher pressures. And then in the 90s, late 80s, early 90s, a group of scientists got pure carbon, nothing but carbon atoms, to come together in a new way. And they made this geodesic dome of carbon. It's 60 carbon atoms in there. And they actually named it after an architect. It's named after the architect Buckminster Fullerene. So they call this, Buckminster Fuller was the architect's name. They call this Buckminster Fullerene. For short, we call these buckyballs, and a 60 carbon atoms there. People were freaking out. Carbon, pretty big deal, right? Organic chemistry just focuses on carbon solely. So we got a whole branch of chemistry deals with carbon-containing molecules. Now we got a new elemental form for carbon. People were freaking out. Slight twist to the story. People thought this was entirely synthetic. But then once they knew what to look for, they have found like milligram quantities of Buckminster Fullerene in the soil and stuff in different places. So it does occur naturally. It's just super rare. And it's people don't entirely know how even it got there. So how did it form? How did it come together? What are the origins of it? So pretty cool. This started the whole nanotube movement, nanomolecules. That was really the Buckminster Fullerene that got that going. So we talked about compounds. So now I want to talk about mixtures. And I like to do this using like a tree diagram. So let's do that. All right. So if you got some paper, I think this is the best way to organize the matter stuff. Here we go. So if we make like one of them like tree webs, you know what I'm saying? Matter can be broken up into two like main branches. You can be a pure substance, and that's actually what we just went through here. Pure substances. So we said pure substances can exist as elements or compounds. And we just listed some examples, iron, iron, O2, S6. We went through that. Compounds, we said, two different types of atoms, something like water, pure water, not tap water. Tap water is going to be a homogeneous mixture, so distilled water, carbon dioxide. So matter can be pure, or it can be a mixture of more than one thing. So the next thing would be mixture. It can be a mixture. And we have two different kinds of mixtures. We're going to have homogeneous mixtures. Some people say homogeneous, homogeneous, and then heterogeneous mixtures. Homogeneous mixtures, we usually don't even use that term. We usually just call them solutions. So homogeneous mixture and solution, they are synonyms. can use them interchangeably. Most of the time, we just call them solutions. Like I'll say, oh, I'm going to make a 2-molar homogeneous mixture of hydrochloric acid. I usually say I'm going to make a 2-molar solution of hydrochloric acid. So what makes a homogeneous mixture a homogeneous mixture? It's got to have one uniform layer. It's got to be the same consistency throughout. So what are some examples of a homogeneous mixture? That would be something like salt water. Salt water contains sodium chloride and H2O. But if you think about it, because salt is soluble in water, sodium chloride dissolves in water. If I add it in there, it dissolves and the sodium chloride dissociates and it's uniformly distributed throughout. It's one uniform consistency. You can't see distinct layers. That's a homogeneous mixture. Many other homogeneous mixtures, apple juice without pulp, orange juice without pulp, coffee without any of the coffee grinds getting through it. Those are all homogeneous mixtures. Doesn't even have to be a liquid. Air is a homogeneous mixture of gases, right? Think of everything that's in the air. You got oxygen, you got carbon dioxide, you got a little bit of carbon monoxide, hopefully not too much, right? You got mostly nitrogen, N2. If it's humid, you got water vapor, you got gaseous water, you got steam in the air. So, I forget, I think it's like 30 different gases. Some of them like xenon, hydrogen, helium, they're very trace amounts. But that's a homogeneous mixture, at least within your room. Now, if you start talking about the atmosphere, there you got layers, and but I'm talking about just within a room, that's a homogeneous mixture of gases. Heterogeneous. Heterogeneous has got distinct layers. Distinct layers. You can see the layers. So this would be something, it could be a solid in a liquid. So it could be, sand in water. Now, if you think about sand, sand is not soluble. So you'd have a layer of sand on the bottom. I got a layer of sand. I got a layer of water. That's a heterogeneous mixture. Oil and water. If I got oil and water, I got oil. The oil is less dense than the water. That's a heterogeneous mixture of two liquids, right? Now, you can, if it's a solid, for example, let's talk about mud. Heterogeneous mixtures can be further subdivided sometimes into suspensions and colloids. A suspension is when you take a solid and you stir it up in a liquid and it's momentarily suspended throughout. Suspensions will always settle back down, and you can expedite that settling by filtering it, right? So like mud is a suspension. You got dirt and water, you mix it up momentarily, it's a suspension, right? Salad dressing. If I want to use Italian dressing, it starts out as a heterogeneous mixture, but you're going to shake it before you use it. Okay, you turn it momentarily into a suspension, so you get all the goodness on your salad, right? Again, if you wait, they'll eventually settle, and you can filter it. Colloid's a little different. A colloid is when you whip that particulate around so much and you get it dispersed so much that it'll never settle back down. It's when the particulate is smaller and not usually visible. So like milk is a colloid. So milk is technically not a homogeneous mixture. There's tiny balls of fat floating throughout there that'll never settle back down. Smoke is a colloid. Fog is a colloid. You can determine if you have a colloid by shining a light into it. That's called the Tyndall effect. So this is why if it's foggy out, you don't put your high beams on because it makes it worse, right? It scatters the light. So there's different kinds of heterogeneous mixtures we don't need to get into, but hopefully you got an idea. All of matter, right, falls into essentially this pretty rudimentary tree diagram that I just drew up here. Again, we got some special cases sometimes, but you're either pure or you're a mixture. If you're pure, you're made up of just one type of atom, you're an element, or you're made up of more than one type of atom, you're a compound, right? And by the way, it doesn't have to always just be two you could be acetic acid, HC2H3O2, right? You can be hydrogen, carbon, and oxygen. You have many different things. And if you're impure, you're a mixture of just one layer, a homogeneous mixture of solution, or you got multiple layers, you're heterogeneous. Cool. So that's what that slide is saying right there. Homogeneous, heterogeneous. There we go. All right, chemical physical properties. Let's do it. A physical property is something you can observe about a substance without changing the substance's composition. These are things like usually you can use your senses to get. So what's the color? What's the odor? Sometimes, like you can be a measurement. What's the volume? What's the height? What's the length? What's the density? Uh, and then ones that people don't think about very often are melting point and boiling point. Those are physical properties. If you think about it, right? Like if I record the temperature that ice melts, I didn't change the chemical composition. It's still water. It's just going from the solid phase to the liquid phase. I get the solid water back just by popping it back in the freezer, right? So then the same with boiling. If I boil a pot of water, I'm just going from liquid water to gaseous water. If I put a bag over it, I could collect the steam, tie it up, shove it in the fridge, and it would recondense. So boiling point and melting point are technically physical properties because you're not changing the composition, you're changing the state, solid, liquid, gas. Chemical properties describe a substance's ability to react. Okay, so this is like a substance's flammability, or if it dissolves in acid, or if it, what's its combustibility, things like that. How does it oxidize? Does it get reduced? Those are all chemical properties of the substance. And in a chemical property, that substance is undergoing a chemical change, which we'll talk about the 5 signs of a chemical change here in a moment. Let's get the 5 signs. Let's do physical change, chemical change. Let's get that all written down. I like to add some to that slide anyway. So let's start with physical changes. Right, physical change. A physical change is a change in an object's size, shape, or state of matter. So, for example, if I take a piece of paper and I change its size and shape, I didn't alter it chemically. It's still the same thing, right? If I rip it in half, it's still the same thing. That's a physical change. Changes in states of matter as well. Solid, liquid, gas. We actually have terms for these, right? So a solid to how do I usually like to do that graphic organizer? Yes, let's do it like this. So we're gonna do solid down here, we're gonna do liquid up here, and we're gonna do gas over here. So we got different terms for this. When a solid turns into a liquid, we call that melting. I should have made this a little bigger, huh? And when a liquid turns into a solid, we call that freezing. You guys already knew that. Those are the easy ones. Get the easy ones out of the way. May I ask you some? How about a liquid to a gas? There's a couple different terms for this. What do we call it when a substance goes from its liquid phase to its gas phase? You think of 3 terms. Talk about which one's the technical term. Anybody? Liquid to a gas. What do we call that? You can type it in the chat too if you don't want to unmute yourself. Try and get a little interaction here, right? It's gonna be some long 4-hour lectures. What do we got? Well, steam is what if you're talking about just water, right? That's gas, but I'm talking about the process of turning a lake. So that Yeah, there we go. Now it's coming. Evaporation, vaporizing. That's the technical term, Brianna. You've taken chem before. I can see that. Yeah, let's talk about this. When we go liquid to gas, the technical term is vaporization. Now, a lot of people say evaporation. I'm okay with that, but let me talk about the distinction. Evaporation is technically when a substance goes from a liquid to a gas below its boiling point, which is crazy. How does that even happen? Yeah, you have to take Chem 102 to figure that out. So, for example, if I leave this water sit out here in this room till Wednesday, there's going to be less of it in here when I come back, especially because this room is above my garage. And if I don't have that air conditioner running, it's about 97 degrees in here. So there's going to be a lot less water in here. But it wasn't at 100 degrees Celsius, right? It was maybe only up to 100 degrees Fahrenheit. Okay, so how did that happen? Yeah, when a substance goes from the liquid phase to the gas phase below its boiling point, that gets into something called Gibbs free energy, and that's called evaporation. But if I'm boiling something, it's called vaporization. Okay, and also sometimes it's called boiling, obviously. Okay, how about the reverse? What do we call it when a substance goes from its gas phase to the liquid phase? So when steam turns into liquid water, what do we call that? Or when the water vapor, which some of you guys use those wonderful terms. Yeah, we call that condensation. There we go. Thanks, guys. Condensation. Excellent. All right, here's the tough ones. Here we go. Let's get the easier of the tough ones out of the way. What do you call it when a substance goes directly from its solid phase to its gas phase without entering the liquid phase? So dry ice, right? If you've ever seen dry ice, you ever get the Omaha steaks or something, right? Okay, they send it with solid carbon dioxide. And at 1 atmosphere of pressure, carbon dioxide cannot be a liquid. It goes directly from solid to gas. What do we call that? Somebody usually knows this one. It's a decent band in the 90s. Lead singer died. Fortunate. They got a new guy, Rome. So this is called sublimation, right? The band was Sublime. So sublimation. You guys are all probably too young, man. How old? I'm getting old now, man. So sublimation is the process of going from the solid phase directly to the gas phase. Okay, obviously, if you order some steaks in the mail, they can't pack it in ice because it's going to ruin everybody else's mail when it melts. They pack it in carbon dioxide, and they're probably going to dry ice solid carbon dioxide, sublimes, becomes a gas, doesn't ruin anybody's mail. The one you probably are not familiar with is when a gas turns back directly into a solid. This is called deposition. Deposition. It's a purification technique. So when you go on to take organic chemistry, sometimes you sublime iodine because the iodine is impure. Iodine cannot be a liquid at 1 atmosphere pressure. So you heat this iodine up, it sublimes into a gas, and then you have you have a test tube with ice sticking in it, and the iodine comes up and deposes onto that cold test tube, and you get needles of pure iodine that grow off of that test tube. It's like super cool, especially because iodine gas is purple. So this purple gas comes off of it, and then it recondenses as these solid metallic looking like needles. It's pretty awesome. Yeah. So these 6 terms, if you see them, it is a dead giveaway that it's a physical change, folks. Dead giveaway, it's a physical change. So melting, freezing, vaporizing, boiling, condensing, deposing, subliming, dead giveaway. It's the same substance. The substance is not changing. It's solid carbon dioxide and it's gaseous carbon dioxide. It's solid water and it's liquid water. It's liquid water and it's steam. Okay, the substance did not chemically change. Okay, it just went from to a different state. All right, let's do chemical change. In a chemical change, you are making a brand new substance. Making a brand new substance. And it's going to have totally different properties. Totally different properties. And when you do this, when you make a brand new substance, there's usually at least 1 of 5 things that has to happen. There's 5 signs of a chemical change. 5 signs of a chemical change. Here we go. The first one and easiest one to remember probably is color change. So if I mix some stuff together, if I take two clear solutions, I mix them together and now it's yellow, I probably made a new substance that has a new physical property that's yellow, right? You know, like I didn't start with a yellow substance. Now I probably got a new substance. So color change is usually a pretty good indication that you had some kind of chemical change going on. Okay. That's the easy one. Let's get that out of the way. Next up, emission of light. So, you know, I've got a glow necklace, right? Okay, and it starts phosphorescing or emitting lights. Okay, fire. I light something on fire. That's got a couple signs of a chemical change, right? But one of them is definitely the light that is coming off of that. A road flare, you know, a match. Okay, you got a chemical change going on there. If you're giving off that much energy, some bonds are being broken, some new bonds are being formed. Yep. Next up, a temperature change. And that could be hot or cold. You mix two things together and it gets cold. That's called an endothermic reaction. We'll get to that in the thermo unit. You guys probably already know that already. Usually they give that to you in bio. Or you mix two things together and it gets hot. That's exothermic, right? If you got a temp change going on, that's a sign of a chemical change. You broke bonds. These two, emission of light and temp change, they deal with energy. And that's because chemical bonds are stored up chemical energy. So there's literally energy stored between the atoms. And we can unleash that energy by breaking and making new bonds. Okay, so these two go together in my mind. The next two go together in my mind as well. So the next one would be emission, or sometimes usually it's called gas evolution. I was going to say emission of a gas. We usually call it gas evolution. So essentially, you make a gas. You mix some stuff together and it creates a gas. What does this usually look like? It usually looks like bubbling and fizzing, right? So, you know, it's that stereotypical baking soda vinegar volcano science fair project, right? So, like if I take baking soda, I pour it in an acid like vinegar, it reacts. One of the things it makes is carbon dioxide. And then that carbon dioxide kind of bubbles out of the solution, right? Same thing when you open a soda, they forced carbon dioxide in there, and those carbon dioxide bubbles that are escaping. Now that's not a chemical reaction, okay? But because it's not at that high pressure, it's escaping. Same idea. If you ever see gas bubbles escaping, probably a chemical change that's taking place. So you probably made a new substance as a gas and it's trying to get out of there. This last one, you probably may have never heard this term before, but trust me, after this class, you're going to become ridiculously familiar with this term. The last one is formation of a precipitate. And precipitate is a fancy word for a solid. If I mix two things together and a solid crashes out, a precipitate crashes out, that's a pretty darn good sign that you made something new. I didn't have this insoluble solid when I started, and now I mix the stuff together and I got an insoluble solid now that's sinking to the bottom. Yeah. These are your 5 signs of a chemical change. If at least one of these things happens, you probably made something new, right? You probably made something new. Now you can get a lot of these happen. Like for example, if you light a log on fire, I mean that's like a color change. That's emitting light. That's a change in temperature, and it's giving off a gas, right? Like that's like everything but the fifth one, formation of precipitate. So they don't have to. It's always just one. You can have multiple. Cool. So we added a bunch to that guy. So take a second here. We got 1 to 8. And some of these are tricky. Like number 6, I want to have a discussion about. Okay. Go through these and if you got a piece of scratch paper, just number 1 to 8 somewhere. And if you think it's a physical change, put a P. If you think it's a chemical change, put a C. What do you want to try and keep in mind? Or do any of these 5 things happen? If not, probably physical. Is it just a change in size, shape, or state of matter? Probably physical. So try 1 through 8 here, and we'll go through it Again, I'm lazy, so you know, just the C or a P is good enough for me on a piece of scratch paper. All right. So here we go. Wood burning. And you can type this in the chat if you want, what you think these are. So wood burning, and you don't have to. We can go through these quickly too if you want. Hopefully these are pretty easy. Why am I not allowed? There we go. My God, every time I log into Zoom is a different toolbar. This is a chemical change, right? We just talked about that. You got 4 of the 5 different signs of a chemical change. This is chemical change. Number 2, keyword here, melting. That makes this physical. Again, if you see one of those 6 change of state words, man, we are talking physical, right? That is just solid H2O going to liquid H2O. It's a change in state. Photosynthesis, that is 1,000% chemical, right? We have not covered reactions yet, but oh boy, will we. Okay, if you've taken bio, photosynthesis is carbon dioxide and water. So 2 different compounds coming together to make a beautiful element called oxygen. Thank goodness for that. And then glucose, which is C6H12O6. I'm not going to write that all out because I'm using a mouse and it sucks. But this is definitely chemical reaction. We're making 2 different things, right? So we're making new stuff, folks. That is a chemical change. Fruit rotting. If you think about it, fruit rotting, that is the fruit, that is the compounds, the sugars in the fruit breaking down, usually giving off a gas called ethylene gas that is the gas comes off of ripening fruit. They use that to their advantage. Ethylene gas causes other fruit to ripen. So if you've heard the phrase one bad apple, that's because it just takes one rotting apple to make the other ones rot really quickly. The fruit industry takes advantage of that. They pick the fruit super green down in like South America or Central America, and then they ship it up here and they ripen it quickly by applying ethylene gas to it. Breaking a rock into smaller pieces, that's just a change in size, shape. So that's a physical change. Number 6 I want to talk about here, dissolving salt in water. Now, some people will say that this is a physical change and that it's entering what's called the aqueous state, okay, which we are going to get into in a decent amount of detail. That's just, when something is dissolved in water, we call it the aqueous state. um, I'm inclined to say, okay, well, when the salt dissolves, let's say sodium chloride dissolves, does it get hot or cold? And if there's a temperature change, we're going to call it a chemical change. And if you actually do it, it gets a little cold. So I call it a chemical change. If you see somebody say it's a physical change, I see where they're coming from. You can get the salt back if we boil the water off. This one people argue over. I'm not going to ask about dissolving in terms of chemical or physical. But my opinion is stick a thermometer in there. Is there a temp change? If so, then yeah, I would say it's chemical. Sanding a table, that's physical. You're just changing the size and shape. And then number 8, alcohol evaporating. That is also just physical. The alcohol is going from the liquid state to the gassy state. You could get it back, put a bag over it, trap it, throw it in the fridge. It'll recondense. So yeah, hopefully you did well there. If not, go back over those. Woo. All right. So that that was like the beginning part, okay, of chapter one. So chapter one is really divided into two parts. Okay. It's got a matter, types of matter, phases of matter, all that stuff. It's got a matter part to it. And now the second part of chapter one is measurements and calculations. So we get into sig figs and we get into dimensional analysis. Okay.